Okay. So, so in the previous class, I introduced the problem of source coding or data compression, and one class of data compression algorithms that we saw was lossless variable length compression. So here the problem is that you have a file of containing n characters or n symbols. We'll assume that each symbol in the file, just one sec. Yeah, so we have a file containing n characters or n symbols. This is what we'll call a source. Each symbol in the source comes from some alphabet script X. We'll assume that the alphabet is finite, and but in general we can take care of discrete alphabets as well. So the goal is to construct these algorithms, the encoder and the decoder, or the compressor and the decompressor. The compressor takes as input the file, the raw file, and outputs a code word of length k. So it's a sequence of k bits. And the decompressor is to, the goal of the decompressor is to recover xn from the code word ck. So we'll allow the size of the compressed file, which is k, to depend on not just n and the distribution itself, but also on the realization of the source. So in general, if xn is random, then the file size is also going to be a random variable depending on xn. And our goal is to design these compression algorithms, F and G, so as to minimize the expected length or sometimes the expected rate. So the rate is defined as, the average rate is defined as the expected code word length divided by n. Okay, so any questions regarding the topics that we covered in the last class? So wait for 10 seconds. Okay, so let's see, what are the requirements of that the compressor and decompressor must satisfy. Now these are variable length compression schemes. So one fundamental requirement is that we should be able to, of course, recover the original file uniquely from the code word. So this property is called non-singularity, and it says that given any two raw files, let's call them x1n and x2n, the compressed files corresponding to these should be different. So if x1 is not equal to x2, then the encoding or the code word or the compressed file corresponding to x1 should not be equal to the compressed file corresponding to x2. So that's a very basic property that we require. Now, since we are allowing variable length compression algorithms, we need to know when the compressed file corresponding to a raw file ends, right? And I mentioned that one way to do this is to store the size of the file as a header. So you can have some header information where you can store the distribution. You can also store the length of the code word and so on. But in many circumstances, this is not desirable because, after all, storing the size of the file is an overhead. So what we will want is that we should be able to say when that particular file ends, or even an even more basic property is that if I concatenate the compressed files corresponding to two raw files, So let us take an x1n and x2n. Now these are two different raw files, right? And I'm going to compress multiple. It could be the case that I'm storing multiple compressed files together, right? And I need to know, and I need to make sure that if I store them next to each other, I still can recover them separately. So if I take f of x1n, the compressed file corresponding to the first one, so let's call it k1, and c2 k2. So if I take these as a binary string together, then I should still be able to get back x1n, x2n. Right? So from the concatenation, I should be able to recover x1n, x2n. So to define this a little more formally, I'll define the extension of a code as the following. So given a compression algorithm, the extension, so the compression algorithm is defined over files of size n. So we fix the file size. So, and if I have multiple files, x1n, x2n, x3n, so on, maybe if I have k files, and I look, then the extension of this is another compression algorithm, which is obtained by taking the compressions of each of these files separately. So this is f of x1n, f of x2n, up to f of xkn. So let us look at this with an example. Okay. Now let's look at something very small, a toy example where n is equal to 1. So let's take n equal to 1, and my alphabet is the set 1, or let's say A, B, C, D. Okay. Now I need to design a compression algorithm. So I need to identify code words corresponding to each of these characters. So let us say that the letter A is encoded by 0. So B is encoded to 1. C is encoded to 0, 1. And D is encoded to 1, 0. Now this is a valid algorithm. This is what the compressor does. And what does the decompressor do? So if it sees a single bit 0, then it outputs A. If it sees 1, then it outputs B. If it sees 0, 1, it outputs C. And if it sees 1, 0, it outputs D. Okay, it's a simple enough compression algorithm. Now, if our only goal is to compress just A, B, C, or D, then this is fine. This is good enough. But now let us say that we want to compress, say, A, B, A. Right? Now, of course, we could separately design a compressor for sequences of length 4, or what I could do is compress each character separately and concatenate it. So the extension of this particular compression algorithm would be so f of AB AA would be so what would this be equal to?
0, 1, 0, 0.
0, 1, 0, 0. Exactly. So this would be 0, 1, 0, 0. Now, do you see a problem with this kind of extension?
It could be mapped as CAA or any other options as well.
Exactly. So if someone gives you, if the decoder is presented with the sequence 0100, then really there is no way to know whether this is ABAA or it could be CAA or it could be ADA, right? So this particular coding scheme, this particular compression algorithm is not uniquely decodable, because for a sequence to be uniquely decodable, every extension should be singular. So a compression algorithm f comma g is uniquely decodable if every extension is non-singular. Okay, and in this particular case, not every extension is non-singular. So for something to be for the extension to be non-singular, if I have x1, x2 up to xk, and I have another, say, x1 prime, x2 prime up to, say, xm prime, then f of x1 through xk should be different from f of x1 prime up to xm prime. And this particular example is not uniquely decodable because f of ABAA is the same as f of CAA, and it is the same as f of ADA. Right? So clearly it's desirable to have a compression algorithm which is uniquely decodable. But in some cases, even this is not good enough, and will require a more stronger property, which is called prefix freeness. So a compression algorithm is said to be prefix free or instantaneous if the code word or if no code word is a prefix of any other code word. Okay, so what do I mean by the prefix?
Sir, you are muted. Sir, you are not audible. Hello, sir.
Right? Am I audible? Okay, great. Yeah, sorry for that disconnection. There was a power cut here. Okay, so as I mentioned, a code word, a coding scheme or a compression algorithm is said to be prefix free or instantaneous if no code word is a prefix of any other code word. So if I take any two code words, then one code word should not be a prefix of the other code word. So what do I mean by the prefix of a particular code word? So a prefix is basically any sequence of symbols which, so for example, if I take 01011, then 01 is a prefix of this code word, 010 is a prefix of this code word, 0101 is a prefix of this code word, 0 itself is a prefix of this code word. Right? So any subsequence of this particular, starting from the very beginning, is a prefix of this code. Okay, so now let's take another example. So let us say that, let's come back to the example of ABCD. So I have 4 characters and I want to design a compression algorithm for ABCD. Okay, so let us take 1 0. So A gets mapped to 1 0, B gets mapped to 0 0, C gets mapped to 1 1, and D gets mapped to 1 1 0. Okay, so is this compression algorithm prefix free?
No, sir.
It is not, right? Because 1 1 is a prefix of 1 1 0. So the code word corresponding to C is a code word corresponding, is a prefix of the code word corresponding to D. Now, is this singular? Is it non-singular? Yes, is it non-singular? Right, it is, right? Because the code words corresponding to any two symbols are different. Is it uniquely decodable? So I see some people saying it is not uniquely decodable. Let us look at the extension. Okay, take any extension AB. What is the compression corresponding to AB? It is 1 0 0 0. Can I uniquely get back AB from this? Yes, right? So take anything else. So let's see. What about CD? Get back? Yes. So where do you think there might be a problem? So some of you mentioned that it is not uniquely decodable, and maybe it is not uniquely decodable, but what kind of a problem can occur? Or if you think it is uniquely decodable, then why do you think it is uniquely decodable?
So for DA, we can decode like that CAA. We will like write DA.
Okay, so if you have DA, which is DA is 110, DA is 11010, right? So this cannot be decoded as CAA, right? Because you know the length. So let's say you have
Yes,
D.
sir. No, sir. I did
So
mistake.
this doesn't happen, right? So maybe what can happen is that, okay, you have DB, which is 1 1 0 0 0, and once you come here, it's you still cannot decode this as let's say CA, right? Because there is 1 0 left over at the end.
So I think this will be uniquely decodable because the prefix issue that we have here is for C and D, and both of them have different bit lengths. So there should not be an issue, at least in this case.
Correct. You're right in identifying that this is indeed uniquely decodable. Uh, so so what? But although this is uniquely decodable, it is not prefix free, and it is not, in some sense, it is not instantaneous in the following sense. Now let us say that I observe the code word 1 1 1 0. Okay. Okay, or maybe this is something better. So let us take 1 1 0 0 0 0 0 0 0. So have, yep. Okay. So suppose that I observe this particular sequence. Okay, this is the encoding of some particular sequence. What is it the encoding of? It is DBBB. So D B B B B. Now consider 1 1 0 0 0 0 0 0. What is this the encoding of? It is CBBB. So if I have, say, 1 1 followed by K zeros, then how would you decode this?
Depending on K is even or odd.
Correct. So depending on whether K is even or odd, you would decode this as either D B B B B B B B. So if the number of zeros is odd, then it would be D followed by a sequence of B's. If the number of zeros is even, then it would be C followed by B's. So unlike let us say the encoding 00011011. So in this case, you know that once you see any two characters, you know what the encoding is, right? But here you need to, in order to say what the first character is, even to decode the very first character, you need to actually go till the end of the code word, the end of the encoding, in order to even identify which the first character is, whether it is 110, whether it is D, or whether it is C. Do you see that? So even if you want to, so let's say you want to decode only the first character of the sequence, okay? I don't care about the entire file itself. I only want to decode the first character. Then in this case, I cannot do it just by seeing the first few bits. I have to go till the end of the sequence because I have to find out how many zeros there are, whether there are even number of zeros or odd number of zeros. Right? So in that sense, it is not quote unquote instantaneous because you have to wait. There is a certain delay in the decoding of the first character. All right. So let us take, in contrast to that, let us take the following example. So you have A, B, CD. Let us encode A by 0. Let us encode B by 10, encode C by 110, and D by 111. Okay. Is this encoding prefix free? It is, right? It is a prefix free encoding. And so let us take, say, something like DBBC. Okay, so what is the encoding of DBBC? Right, so it is 111, 1010, and 110. Right? Now, if I want to decode this particular sequence, then I start with the first symbol, first code word symbol. It is 1. Then so it can be either B or C or D. Then I see the next character. It is 1 1. I immediately know that it is either C or D. I see the third one is a 1. So I immediately know that the first character is a D. I don't need to look at the encoding of the rest of the sequence in order to identify the first character. So in some sense, there is absolutely no lag, there is no delay in the decoding of the first character, or any character for that matter, right? So that is not what is happening in this particular example, which is where it is uniquely decodable but not prefix free. So in this case, I may need to go till the end of the sequence in order to decode even the first symbol. All right. Any questions?
Excuse me, sir, but in a real
Yes.
system, how is the decoding done? Is it done with all the bits at one time, or do we do it individually?
So again, it depends on the implementation of the compression algorithm. What are typically used in most scenarios are prefix-free algorithms. So typically, you don't want any delay, and something of this sort would be preferred over a uniquely decodable code. Now, note that every uniquely decodable code, sorry, every prefix-free code has to be uniquely decodable. So it may happen. So there is no reason why one would want to choose a uniquely decodable code which is not prefix-free. The only reason why one may want to think about using a uniquely decodable code which is prefix-free, which is not prefix-free, would be if you can somehow reduce the compression length, right? So, but it turns out that the minimum rate of compression that you can achieve using any uniquely decodable code is the same as the minimum rate of compression that you can achieve using a prefix-free code. So you might as well ask for a prefix-free code itself, because it's easier to encode and to decode.
Okay, thank you, sir.
Any other questions?
Sir, you said that even if it's a prefix, even if there are prefixes and it is uniquely decodable, it's still gonna be equivalent to the best case of
Yes.
prefix-free encoding.
Yes.
Is there like, will we be discussing the proof of that?
Correct. Yes, we will.
Okay.
So in some sense, so we'll see that every prefix-free code has to satisfy something called a Crafts inequality, and every uniquely decodable code also has to satisfy the same inequality.
Okay. And sir,
Yes, please.
sir, is there any like even inside the prefix-free the codes which have prefixes, there is two classes, right? One which is uniquely decodable and one which is not. Do we distinguish them, or we don't
So-
study any of them?
So at the very minimum, we want it to be uniquely decodable, right?
Yeah.
Because otherwise, I mean, how do you know when the first, so if it is not uniquely decodable, then as we've seen in this particular example, so AB, the encoding of ABAA is the same as the encoding of CAA. So if you see 0100, then you won't be able to decode uniquely. So then it doesn't become very useful, right?
Thank you.
So typically so henceforth we will really demand that the code, the compression algorithm that we design should be prefix free.
Hello, sir.
Yes, Shantanu.
So, like for a code to be instantaneous, we will have to first consider number of bits which will be equal to the maximum bits of a alphabet, right?
Sorry, could you please repeat? What do you mean?
So, like for example, in this question,
Yes,
the maximum number of bits assigned to an alphabet are 3.
correct.
So, like to consider to check whether this code is instantaneous or not, we will have to first check 3 bits.
So not necessarily, right? So typically, how do you decode? You decode it in sort of an online fashion. You first look at the first symbol, the first bit, and then the second bit, and then the third bit, and at each bit you make a decision. If you can decode at the current bit, then you decode. If you cannot, then you look at the next bit, and so on.
Okay, so like, but then if the number of bits in the sequence are only 3.
If the number of bits in the sequence
For
is
example,
3,
in this
okay,
example, it's
Yes.
only 1, 1, 1.
correct. Okay, so if you have only 1, 1, 1,
So we will have to check all the 3 bits before getting to the final conclusion.
correct, of course.
And so, sir, this will again not be instantaneous, right? Because then we have to go through all the bits in order to come to the conclusion.
Yes, but then this is the encoding of a single symbol, right? It is the encoding of only just D. Right?
Okay, sir. Yes.
So take that in opposition to this particular example over here, where technically the first 3 bits should be sufficient. So in this case, the maximum number of bits that you'll anyway have to probe is 3 in order to decode any symbol. Whereas here, in principle, you may need to decode, you may need to probe an infinite number of bits even to decode the first C or the first D, right?
Yes, sir. Got it. Thank you.
हेलो सर
Yes, yes, sir.
सर ये in uniquely decodable scheme you said that we have the lagging since we
Correct.
have to go through all the bits for getting the information about the header so
Not the
sir,
header, the first symbol itself. It's not the
yes,
header.
sir, first so okay sir the first symbol but if we consider all the symbols then in the both the case we will have the same lag.
Not really, right? So let us take this particular the example over here. So 111 1010 110. Okay. So if I want to decode only the first character, then I can do it just by looking at the first 3 bits. Right? I don't really have to read any of these bits. I don't have to read in the future in order to decode the first character over here, which is D. Right? So how will decoding work? I'll first see the first bit of the code word. It is 1. The second bit is 1. Can I decode at this point? I can't, because it's either C or D. I'm not sure which it is. So I look at the next bit. It is 1. Now can I make a decision? I can, because it is D. Right? And now let us say that the next bit that I see is 0. Okay? The next bit is 0. Can I decode at this point?
Yes A.
It is A, correct? Now let us say that the next bit that I see is 1. Can I decode?
No sir, we have
You
to
can't.
see.
right?
Yeah.
Now suppose that I see a 0. Can I decode?
Yes, sir, it is B.
It is B, and so on, right? So in that sense, you can immediately say whether, so it's either a binary decision, either you can decode, or you're sure that it is not a certain, not some of these symbols, right? So if you want to decode D, then at max you'll have to see 3 bits. You don't have to see in the future, right? You don't
Okay,
have to see
fine,
the
sir.
encoding of the next symbol in order to decode the current symbol.
Okay, so and in on contrast, in uniquely decodable scheme, we have to see all the symbols.
Correct. You may have to see. You may have to look at the encoding of the next symbol in order to decode the current symbol. If it is uniquely decodable but not prefix free.
Okay, sir, got it.
Okay.
So one last thing. Uh, so if a code is prefix free, then it implies it's instantaneous. Huh?
So these are two different names of the same thing. So it's called either prefix free or instantaneous. And yes, so of course these two have different meanings. Instantaneous in the sense that you can immediately decode, and prefix free that it is not a prefix of the other. And yes, if it is prefix free, then it is instantaneous.
And so, like, if it's not prefix free, then it may or may not be instantaneous. Is that so, sir?
No. So if it is not prefix free, then it turns out that it is not instantaneous.
Okay, sir. Okay. No.
Right. Any other questions? Okay, so this is a good time to have a quiz, a very short quiz. So I'll put the link for the quiz in the chat box. You can take maybe 3 to 4 minutes to solve this. Let me know in case you're not able to access the quiz form. Sorry, are you able to access the quiz?
Yes, sir.
So yes, it is weak. So everything is lossless coding. So I'll stop taking responses in a minute. So please fill in your quiz. Okay, so is there anyone who has not submitted their quiz yet? Anyone who hasn't submitted? Okay. Okay, so let's continue. Yeah. So we've seen three sort of properties in increasing order of strictness. So first, non-singular, which is a very basic requirement. So if it has to be lossless, then it has to be a non-singular code. It could be uniquely decodable, and the sort of the best requirement, the best case scenario, if it is if it is prefix free or instantaneous. Okay. So let us first, yeah. So now let's discuss an asymptotically optimal scheme. So if n is large, so my goal is to design a coding scheme which minimizes the rate. R should be equal, so the R that I want to achieve, so this is the expected value of K of n px xn divided by n. And in fact, this particular scheme works irrespective of whether it is IID, whether it is memoryless or it has memory or not. As long as it is stationary and ergodic, this will give the best possible rate. And in the information theory course, you've seen that the optimal rate of compression for asymptotically large n is equal to the entropy rate. You may not have seen a proof of this, but the best possible rate that you can achieve is equal to the limit as n tends to infinity of h of xn over n. And now we'll try to design a lossless compression algorithm which achieves this particular rate. Okay, so the way I'm going to construct this compression algorithm is the following. Now, my code word corresponding to each xn is going to consist of two parts. So it's a variable length scheme, so the lengths corresponding to different code words could be different. So the code word is going to consist of two parts, a header and the actual sequence of compressed bits. Of compressed bits, or which is going to be a code word. Okay, so let me call it ch and cs. Okay, the header is going to be a fixed length encoding, so it's going to basically be so the sequence of compressed bits could potentially have different lengths. Okay, so what I'm going to do is that in the header I'm going to store the length of the compressed bits. Okay, so this is going to be stored as the header, and to do this I'm going to use order log n bits. So in fact, maximum of ceil of log n bits will suffice. Okay, or maybe some constant times log n. So it's going to be order log n. Okay. So now I need to assign different lengths, so different code words CS for each sequence. And how do I do this? I'm going to write all the sequences in decreasing order of probability. So x1n, x2n, x3n, and so on, such that p of x1n is greater than or equal to p of x2n, which is greater than or equal to p of x3n, and so on. Right? And for each of these, I'm going to identify a code word. Now, clearly, if I want to design a good compression algorithm, then x1n should get a code word which has length which is smaller than or equal to that of x2n, and for that it should be smaller than or equal to that of x3n, and so on. So the lengths should keep increasing as I go from top to bottom, because the probability goes on decreasing as I go from top to bottom. Okay, so for x1n, I'm going to consider the sequence of length 0. So basically, I'm going to encode nothing. So it has length 0. For x2n, it's going to be a sequence just 0. That is going to be the encoding of x2n. So this is CS and this is xn. For x3n, it's going to be 1. For x4, it is going to be 0, 0. For x5, it is going to be 0, 1. And then 1, 0, 1, 1, and so on. It's going to be 0, 0, 0, 0, 0, 1. So basically what I'm doing is that I'm populating this table from top to bottom with all possible sequences of length 0, then all possible sequences of length 1, then all possible sequences of length 2, all possible sequences of length 3, and so on. All right. But then I'm also, as the header, I'm storing the length of this sequence. So for example, if I want to encode x1n, this is going to be encoded as the encoding of 0 using log n bits, and then that's it. I don't store anything extra. If I want to encode x2n, then basically I'm going to store the compressed file corresponding to x2n is going to be the encoding of 1, because it's a sequence of length 1. So I'm going to use log n bits to encode 1, and then I'm going to store a 0. For x3n, I'm going to store the encoding of 1 followed by a 1, bit 1. For x4n, I'm going to store the encoding of 2, because the encoding contains 2 bits, followed by 0, 0, and so on. Right? So I'm going to store the length followed by the encoding of CS as I've described over here. All right. So any questions regarding this particular encoding scheme?
Sir, usually when we store that header,
Yes.
it also will be stored in the form of binary digits.
Exactly. So I'm just going to store the binary representation of 0, binary representation of 1, binary representation of 2, and so on.
Okay.
That's it. But I'm going to use log n bits to store this binary representation, because the maximum value is going to be 2 to, so the maximum number that I will need to store is at most 2 to the n. Right? Sorry, it's going to be at most n. So I will be able to encode this using n bits. Sorry. Okay. So my bad. So what is the maximum number of bits that I will need to store? So okay. So in other words, if I encode using this particular format, then what is the maximum length of the sequence? What is the maximum length of the CS sequence? Even a rough upper bound is good enough. I don't necessarily want you to calculate the exact value. Is it floor of just log n or something else? Is there some other constant factor over there?
Sir, is it starting from 1 or 0?
Sorry? So it's starting from 1. x1n is the empty set. x2n is 0.
So it is okay.
No, not because of the header length or anything. Okay, so it's
Sorry.
just that. Yes, please. Yeah.
It is log n, right? Log 2, log 3. Both of them are floor of it as 1 and
Sure.
4, 5, 6, and 7.
Sure, but you're missing something else, and the something else is that the input file need not be binary.
Oh,
Right? So how many possible sequences are there? So how many possible xn's do we have? The input file need not be binary. It could be non-binary.
So number of symbols power n.
Correct. So it's cardinality of x to the power n. So the number of bits you would need to represent each of these would be log cardinality of x to the power n, or roughly n log cardinality of x. These would be the number of bits, but then we want to store the length of the sequence. So it is log of, roughly log of n log cardinality of x. So this would be approximately log n plus log cardinality of x. Right? So maybe the factor, there's just maybe 1 or 2 bits in addition. Right? So this would be at most ceil of this. So ceil of, so this would be the maximum number of bits that you would need to store the header. So it's still roughly log n. So it's order log n bits. So basically I'm going to store the binary representation of the length of CS as the header. Okay. So now that we have this, okay. So now if I have xin, right, what is the length of the code word corresponding to xin? Yes.
Log I
it's-
base 2.
Correct. So it's floor of log I to the base 2. Right? So this is the length of x. So this gets mapped to a sequence of length log I to base 2. Correct. And so k is basically order log n plus log I to the base 2. Right? So this is at most order log n plus log I to the base 2. Now my claim, so I leave you to verify this, is that the probability of xin is always greater than or equal to 1 over I. All right. So I claim that the probability of any xin, if we are ordering it, note that x1n is the sequence with the highest probability, x2n has second highest probability, and so on. So xin has probability at least 1 over I. And if this is indeed true, then I is less than or equal to 1 over probability of xn, which will ensure that the expected length is at most order log n plus the expected value of log 1 over pxn, which is at most order log n plus the entropy of xn. All right. So the achievable rate is therefore equal to the entropy rate, because this divided by n tends to the entropy rate. Because order log n by n tends to 0 as n tends to infinity. Okay. So anyway, so officially we'll end the class over here, but I can take questions.
Sir, there's a small
Yes, Anara.
doubt. Sir.
Yes, please.
If the entropy is higher, number of bits required for each alphabet will be higher, right?
If the entropy is higher than the number of bits, what do you mean by the number of bits need to be higher?
Amount of information contained in each alphabet.
Yes.
Number of bits required to represent that alphabet in a compressed form of it.
Yes. So the expected number of bits could be higher. Note that. So here this is so for example, the encoding over here, we are doing the same. So for example, if you have a certain alphabet, then it's always the same encoding rule, right? It is just the order of assignment which changes.
Yes, sir.
Correct. These lengths are going to be the same.
Yes, sir. So my question
Yes.
is, if the entropy is higher, shouldn't the compressed file size be higher?
So the expected file size will be higher.
But why was the quiz's answer in the reverse form, the second question?
Sorry. Sorry, which question?
We just had a quiz, right? That
Correct.
the second question, size of compressed file for x1 is higher than x2, right?
So we're talking about sequences there, right? So what we were given was that the probability of x1 is 0.2, the probability of x2 is 0.01.
Okay, those are not Bernoulli random variables with the factor 0.2.
No.
Okay.
No. So P of x1 is 0.2, not the entropy. The probability is 0.2. P of x1 is 0.1, and you're assigning code words to each of these.
Sir, it was 0.01.
Okay, whatever. That doesn't matter. So assigning code words to each of these individual sequences.
Okay. Okay, thank you, sir. It was mentioned compressed file, so I got confused if it was the random variable itself. Thank you.
Any other questions?
Sir, I have a general question on
Yes, Anurag.
what we discussed, but sir, suppose there is a source which is sending me packets in some compressed form,
Okay.
using some compressor, and
Okay.
to send those packets to another destination in a different compressed form.
Okay.
So, is there some work done between interoperability of compressors and decompressors, like, or should I just decompress it and then compress it?
But again, so why would you want to compress it in a different form?
Because not everyone may use. So my example is I'm downloading a movie from, say, some torrent site,
Okay.
and I want to upload it to Google Drive instantaneously as each packet arrives.
Okay.
Because we cannot deconstruct it completely unless all of the packets arrive.
True.
And we're not guaranteed that both torrent site and Google Drive use the same compressor and
True.
decompression formats.
Yes. Yes.
In that case.
Yes. So, okay. So, well, this is something which to some extent has been studied. So one way to formulate this problem would be the following. You have a file, xn, and then you sort of partition it into smaller chunks, right?
Yeah.
Basically, what you get is the compressed form of each of these chunks. Correct? This would be what you would get from each of your peers. So this would be sort of each packet in some sense, right?
Yes.
So you would get these compressed forms, and your goal is to somehow, so once you get each of these, you want to obtain the compressed version of all of these, right? So basically what you want is a compressed version of xn given the compressed versions of x1n, x2n, up to whatever xkn. Right. So again, it depends on exactly how you formulate the problem. I guess what you want is given each of these in some particular sequence, you should be able to reconstruct it, because otherwise, of course, you could always decompress each of these separately and then re-encode all of these. Correct? Do I understand the question correctly?
So I don't get the last part. Like I need to use a different compression on x of n. So
correct. So you will anyway, most probably you will need to decompress each of these xins. So okay, so the question is, should I wait for all the packets before compressing this entire sequence, or should I do it on the fly? So as soon as I get a particular packet, I compress, and then when I get the next packet, I update this. I get the third packet, I update this, and so on. Is that the problem that you're asking? Or is it that I can wait for all the packets to come together and then the goal is to then compress everything?
both of them. Like my first question was, should I need to wait for all of the packets to arrive? And that was answered in today's class. Like we can do, because we can do it instantly, we can just decompress each and compress them again.
True. So there's another caveat to that. So if you can indeed do it, but it will be suboptimal. So the compressed length for xn would be larger if you took each of these and concatenated. You could do it. It's a valid algorithm and you can do it instantaneously. But the problem is that the overall compression length, it is still rate optimal or close to rate optimal. But in terms of the actual compressed length, it is still significantly large. If xn is large and the size of each packet is small. So in the case where you're saying it is still sort of work in progress, there are people working on it. But now if you ask the other question, that you can wait for all of the packets to come and then compress together, then the best option would of course be to decompress each of these packets individually and then combine them and then compress. That will always give you the best solution.
Sir, I think you just discussed we first divide the data file and then compress each packet, right?
You divide the file and compress each packet, yes.
No, I was asking the other way around. So like we have a file, we compressed it, and we are sending the compressed form in the form of packets. Like divide the compressed file itself. That would.
Oh, okay. So that is your problem. Okay. So you're compressing the file first, and then you're dividing it into packets. Okay. So then what is the problem?
Then suppose after receiving them, I need to use a different compression algorithm and send it to in a different form.
But why would you want to use a different compression algorithm?
So like I mentioned, right, Google Drive may be using a different way in which if I upload something, it may compress it in a different form and send there.
Okay.
I cannot dictate what decompressor Google Drive uses, right? On its end.
Sure. So then it really depends, right? In general, no, you cannot. You will have to decompress and then recompress.
Okay. So like.
So broadly speaking, your problem is the following: you have XN, you're compressing using, say, just as a simple example, you're compressing using RAR, and you get CK. But now you want to sort of get the zip version of this to get a CK tilde, right?
Yeah.
The question is, can I go from CK to CK tilde directly?
Yeah.
Right. This again depends on the specifics of each compression algorithm used. But in general, you will have to decompress and then recompress. But there are certain sort of blocks in the compression algorithms which are common to different compressors. And so you need not run all the steps of the algorithm. You could do some part of it.
Sorry, sir. Yeah. Thank you.
Any other questions? Okay, so if not, then we'll end the meeting for today.